Light is really exciting. I mean, literally exciting. Light is just little packets of energy called photons traveling in waves. Different wavelengths of light have different amounts of energy in those photons. And if a photon has kind of the perfect amount of energy for a molecule's electrons to get excited, that molecule will absorb that light. This is going to excite the electrons in that molecule. They go from a ground state, they're kind of bored state, to a higher energy level, an excited state. But they can't stay there forever, and so eventually they'll have to get bored and fall back down to the ground state. In doing so, they're going to have to let back off the energy that they absorbed from that light that came in. Sometimes they're going to do this in the form of light. And typically that's going to be a different wavelength of light. Typically it's going to be a lower energy wavelength of light because the process isn't going to be fully efficient. And we'll get much more into the details, but basically they can absorb one wavelength of light and let off another wavelength of light. We call molecules that do this fluorophores, and we call this process fluorescence. Now, a lot of times molecules will just absorb light and not give anything off other than heat. So those would be like non-radiative processes. But the fluorescence is when specifically it's going to give off light. Unless, of course, there's something that's actually stealing their light, or at least the energy that would have been the light. And that comes into play with something called FRET that we'll get into, where you have two molecules and one absorbs one wavelength and lets off a wavelength that's equal in energy to the wavelength of the light that the other molecule would absorb. And so then if those molecules are close, that second molecule is going to steal the energy from that first molecule. And then the second molecule is going to give off light based on the energy it got from that first molecule. This allows you to do things like see if the molecules are close together or far apart, and various cool things that we'll get into. There's also something called quench fluorescence, where there are quenchers, which they don't let off light, but they're able to steal the energy that one molecule would have given off. In that case, the first molecule, you're not actually going to see the light it gave off because the energy that would have been the light is stolen right away. So that second atom is just getting excited from the energy of the first, not from the energy of the form of a light. There are other ways that molecules can get their electrons excited and give off light. And overall, we call this luminescence. So luminescence is just when an electron gets excited and then it falls back down and lets off light. And so fluorescence is one form of luminescence, and that's specifically when the energy that excites the electrons is coming from light. There are also, you can have the energy coming from a chemical reaction, in which case we would call this chemiluminescence. And you will see things like bioluminescence, where you have the reaction catalyzed by an enzyme. A couple of common forms of bioluminescence that you might come across are HRP, horseradish peroxidase, as well as various sorts of luciferase. So you might see like firefly luciferase, you might see renilla luciferase. What these have in common is that there's some kind of boring chemical that you add that then the enzyme is going to convert into a form that gives off light. And the giving off of light, you'll be able to detect. And so in the case of horseradish peroxidase, often what you do is you use this with some sort of antibody conjugation. So you have a little protein that recognizes a protein of interest, and then on the end of that protein, you have a horseradish peroxidase, and then you add a chemical, and then if your molecule was present, then the horseradish peroxidase will be bound to your molecule, indirectly at least, and give off light that you can then see. With firefly luciferase, you give it a different type of substrate, and it can also be used to detect various things that are present, such as oxygen or ATP, if those are needed for a reaction. And so various cool things that you can do with chemiluminescence, and lots there that we're just not going to get into. But the bottom line is that you have some enzyme that's able to convert a non-luminescent thing into a luminescent thing, and then you see light. So as I mentioned, light is little packets of energy traveling in waves. And I was talking about different wavelengths. Well, the wavelength corresponds to how much energy is in those photons. You're probably familiar with the speed of light, so c. Well, you might not know the exact number of c, but the concept that light travels at a set rate. And so if light is traveling at the same speed, but these different wavelengths of light have different amounts of energy in their photons, they're going to have to travel at different wavelengths. So if you think about like a slalom, where the skiers are going down the hill and they're making those big S's. If that skier's got a ton of energy, well, it might make more S's. And if the skier's going slower, it's going to make fewer S's. But maybe it still gets back to the bottom at the same amount at the same time because, well, if you're doing a lot more S's, you're going to have to be going back and forth a lot more rather than just straight down. So overall, you might end up back at the bottom at the same time, but one of you, the person with more energy, would have done more of the S's in the path. How frequently you're doing those S's, that's going to be your frequency. So the more energy you have, the higher your frequency is going to be. Another way you can think about it is if you have kind of a little kid running alongside, walking with his grandpa, and the grandpa's going slow and the little kid's has a bunch of energy, so he's running back and forth and back and forth and back and forth, or not back and forth, but side to side, and they're still going at the same overall pace, but the little kid is going up right and left and right and left and right and left, whereas the grandpa's going more at a steady rate through. So more energy, higher frequency. And if you have higher frequency, but you're still having to go the same overall rate, well, now your wavelength, the distance between those little S's is going to be shorter. So higher energy, higher frequency, shorter wavelength, lower energy, lower frequency, longer wavelength. Different amounts of energy, though. That's what's really important about the differences between the wavelengths, because it's those differences in energy that are going to allow for having different wavelengths of light match different molecules in terms of what those molecules will absorb. Because those different molecules, well, they're going to have different atomic floor plans where those energy levels that electrons can occupy are. So going back to our idea of these electrons kind of occupying energy levels, you often see these things called Jablonski diagrams. So in a Jablonski diagram, it basically shows you the different electron energy levels, the different energy levels that electrons can occupy. And well, it turns out they can only occupy these distinct levels. There's a little bit of wiggle room. However, they can only go from one energy level to another. They can't occupy the space that's in between. I like to think of it as a kind of apartment building. And so these energy levels, these states, so the ground state's your bottom, and then you can have excited states. These different states are kind of like floors on an apartment building. That's why I called it kind of like a floor plan, because, well, the kind of floors are going to be different spacings apart in these different buildings. But you can't just levitate in between the floors. You can only go from one floor to the next. You can think of kind of an elevator, assuming your elevator never gets stuck. Well, it would be going from one floor to the next, but you can't just occupy the space in between. Similarly, these electrons cannot occupy energy levels that are in between the states. There's some wiggle room. You can think of kind of if you start on a bed versus starting on a table versus starting on a dresser. Basically, there's a little bit of difference. These things called vibrational levels that are around these set energy states. This means that different atoms, different molecules will have different energy levels, different distances between the floors, different amounts of energy that is required to jump from one floor to the next. And they can only absorb light if that light is going to get them the perfect amount of energy to jump from one floor to the next. So if you only had enough light to, say, jump from here to here, well, then that light wouldn't be absorbed, because the molecule, if it absorbed that light, the electron would be in the no occupation zone. So it can only absorb light that will get it from one floor to the next. And then again, you have those vibrational levels, so you don't just absorb one specific wavelength, but you will probably absorb a kind of this more wiggle room around it, so you get this kind of spectrum, or you get this kind of diffuse peak rather than one sharp line. You also see that for molecules, you're going to see different peaks, so different absorbance maxima. And this is because there's lots of parts of molecules that can absorb light. If we talk about what part of a molecule absorbing light, we often call this a chromafluor. And because different molecules are complex, they get multiple peaks. And this can allow you to kind of tell molecules apart. And all of that is coming down, remember, to how close together these energy levels are, and therefore how much energy is needed to get to the next level. And you can imagine that you need more energy to go a bigger jump and less energy to go a smaller jump. So between levels that are closer together. If you have conjugation, so conjugation resonance, when those atoms that are connected are sharing the electrons kind of communally, this makes it so those energy levels are close together. And when those energy levels are close together, well, that's going to mean that you don't need as much energy in order to jump to the next level, which means that, well, if we think about what type of light has a low energy level, we're thinking about things with a lower frequency, things with a longer wavelength. And if we look at our electromagnetic radiation spectrum, we can see that. So visible light is only this tiny little portion here. And in this visible light, you can see that we kind of have these wavelengths of about 400 to 700 nanometers. So remember, a nanometer, that's a billionth of a meter. So really, really tiny, but actually not that tiny when it comes to other forms of light like ultraviolet, which we'll look at in a minute. But in this visible light, if you were to steal part of that light, you would actually be able to tell with your eyes. Because white light, say, is the combination of all of these. If you take away some of that light, well, now you're going to see kind of what was left over. And so objects are going to appear the opposite color they appear on the color wheel. If they absorb green light, they'll look red. If they absorb red light, they'll look. And so that allows you to actually see something. And often these molecules where we can actually see them, see a color from absorbance. So at this point, we're not talking about fluorescence, we're just talking about absorbance. If they're stealing visible light, then we're going to be able to see the molecule will look colored. And this is often the case with dyes, where they have extensive conjugation. You often see with dyes, you're going to see a lot of resonance stabilized rings. Those are going to be lowering the differences between the levels, making them closer together, making it so that you can absorb that lower energy light and still have enough to excite. For a lot of our biological molecules, so things like nucleic acids and proteins, they're going to absorb higher energy light. Their electron energy states are going to be farther apart, so they're going to need more energy in order to excite them. If we're talking about more energy, well, now we're going to be a higher frequency, a shorter wavelength of light. And that will take us into this ultraviolet range. We're not able to detect them stealing the light in that range unless we use a machine. We can't tell with just our eyes. And that's why we need to use like UV spectroscopy. But because molecules can still have in this UV range, they can still have like absorbance maximum peaks and things, we're still able to use the absorption from different molecules in order to identify molecules. And we can use Beer's law to figure out the concentration based on how much light they absorb at different wavelengths. So that was just kind of like absorption, but now let's get to the fun stuff. Let's get to the fluorescence. So yeah, you could just kind of like fizzle out and give off heat, but that's really boring. Giving off light is so cool, right? So let's talk about that. Let's talk about the fluorescence. First of all, I should say that it's, again, here we're going to have some wiggle room. There's this thing called vibrational relaxation. If you absorb energy that's going to get you to above the ground floor, so maybe you think about you go from the ground on one floor to the dresser on the other floor, and then you kind of like fizzle back down to the ground, and then you fall back to the ground, to the floor below. What's going to happen is that then the energy is going to be a little less than you absorb. And either way, the process isn't totally efficient. And so the amount of energy you give back off as light is going to be less than the amount of energy that you absorbed as light, or through whatever other energy generating process you absorb light from. So maybe it was a chemical reaction. Maybe you got the energy from FRET. Maybe you got it from an enzymatic reaction. In any of these cases, you're going to get some amount of energy, and then if you let out radiation, if you let off light when you fall back down, then that light is going to be of a longer wavelength. Remember, that's lower energy, lower frequency. So you absorb light of one wavelength, you let off light of a different wavelength, and the kind of difference between those two is a value called the Stokes shift. And the value where they kind of like overlap, your absorbance and your emission overlap, this is going to be a less useful region, and this is going to be your spectral overlap region. when you're looking for like a fluorophore, you typically want there to be a big difference between your absorbance and your emission so that you can tell them apart and so that the emission isn't going to be then being absorbed, which wouldn't be very helpful. What is helpful is if you have these distinct absorbance and emission that you know, and you can shine wavelength at the light that you know that it absorbs, and then measure the wavelength at the light that it emits. So for example, GFP, green fluorescence protein, which we'll talk more about in a minute, is going to absorb maximally at 395 nanometers, so in the UV range, and let off light at maximum emission at 501 nanometers, which is in the green range. And that's why we see green with GFP. As to how structurally it's doing it, it's actually really cool because a lot of fluorophores are going to be like small molecules. But GFP, this green fluorescent protein, it actually has like a kind of built-in fluorophore in the protein itself. You get this cool like cyclized bond between this glycine and this serine. This then gets resonance stabilized. So remember resonance, we're lowering the energy costs to go between the electron states, making it easier to excite it. This is going to make it so that it is going to absorb light and then it will let off light. And so if you look at a plot like this, where you see an emission and an absorption, even though it doesn't label, it's not telling us like which is the emission and which is the absorption. Well, we know that it's probably going to be absorbing light that's at a higher frequency, a higher energy than the light it gives off. If it has a higher frequency, what does that mean about its wavelength? That's going to mean it's got a lower wavelength. If it's got a lower wavelength, well, that's going to be our curve over here. So this would be our absorption, and this would be our emission. Our excitation, our absorbance, same idea. Because remember that it's absorbing light and that's exciting the electrons to a higher energy level. So this is going to be our excitation. And then this one, well, this one's going to have a longer wavelength. It's going to be lower energy. This is going to be our emission. So if we were setting up our detector to detect GFP, we would want to have it so that we would be detecting about like 500 or 20 or so, and that we would be exciting it at about 400. So you can see that it kind of has this really broad excitation profile. This is actually a paper coming from Martin Chaffee et al. This work on GFP got the Nobel Prize because GFP is so helpful in biochemistry for a variety of different reasons we'll get into. But it wasn't perfect to begin with. Not really ideal for what you'd want. And it's also absorbing in wavelengths that a bunch of other stuff absorbs in. So they wanted to see if they could make changes that could make it have better properties for uses as a fluorophore. And so because the fluorophore in the GFP is coming from the protein itself, they thought, okay, well, what if we make some mutations around here? Can we get it so that it's absorbing at different wavelengths or emitting different wavelengths? And because those electron energy levels are so context dependent, so it's not like you could just say, okay, well, this atom is always absorbing this, but it's more like, well, if it's attached to this, then it does this. If it's attached to this, it does this. If it's this nearby, it does this. So it gets really complicated. But that complication, we don't need to worry about right now. We just need to worry about the fact that it works. So this is from Chen's Nobel Prize lecture, showing some of the mutations that they made in order to try to improve the properties. And so here they're looking at serine 65 and looking and seeing how changing that to a threonine or a cysteine or an alanine affected the excitation profile. You can see that when they made these changes, well here, so in this dotted line, this was the wild type, and here when they made these changes, they were able to shift the excitation curves. Because remember that what light wavelengths they absorb is going to depend on the orbital layout based on how the different atoms in the molecule are arranged and interacting. So that's great and all, but could we be greedy and get different colors too? Yes, so through a lot of trial and error and brute force, scientists have been able to introduce changes to allow them to get a lot of different colors. So you make a change, see does the color change, then you get this whole variety of colors to choose from. You make this serine 65 to threonine and you get brighter green. You make the tyrosine 66 to histidine and you get a blue. You make this Y66, so Y tyrosine 66 to tryptophan, and that's going to make it this kind of cyan. And this T203Y, threonine 203 to a tyrosine, that's going to give you YFP. And I know it looks a little weird. It doesn't look that yellow right here, but actually YFP, yellow fluorescent protein, really does look yellow when you see it in the wild. So in grad school, I did a lot of recombinant protein expression using baculoviruses, so using insect cells. And we wanted to be able to monitor if the insect cells were actually making our protein. So we used a YFP reporter. Basically, we told the cells to, at the same time it was making our protein, we said, make this YFP so we can see that you're actually at least got the virus and you're making proteins. And well, it made YFP and it was really pretty. And it allowed us to see that the virus got into the cells and the cells were making the protein. There are also all sorts of other variations on these. So you might see eGFP, enhanced GFP. In addition to making changes to that original GFP, which was coming from a jellyfish, so that protein is actually a protein jellyfish make, and this GFP was particularly coming from Aquaria victoria, and so scientists have looked to other jellyfish and other creatures to see if there are alternative starting points, and there are. Very cool stuff, lots and lots of colors. Some of them have really cool names. There are a lot of fruit names. Cool stuff, You can do things like attach them onto proteins in order to track those proteins through cells. Because remember, this is just coming from the protein. You can kind of just, like we kind of put a his tag on proteins, we can put a GFP tag onto proteins. But that's going to make it kind of big, so sometimes that might not be your best option, and sometimes you're going to want to go with like a small molecule fluorophore. And so we'll talk more about these sorts of things. Why is it good to have a bunch of different proteins? You might want to monitor different things at the same time, maybe track multiple proteins within a cell, or have different cell types light up in different colors. Very cool stuff if you have different colors. And you can also have colors that aren't going to interfere with other colors. So having a lot of options is great. Fluorophores can be proteins like GFP and YFP and all of those fun fruit names, or they can be small molecules. So this is showing things to scale. So this is the size of an antibody. You can see this is VFP. It's Verde fluorescent protein, which is a form of GFP. These are small molecule dyes. This is streptavidin, our good friend streptavidin, which remember binds to biotin really, really tight. Here are some examples. So you can have various dyes as well as various proteins, and each of these will have a characteristic absorbance and emission wavelength. One of the ways that having a lot of options is great is by being able to combine different fluorophores to do FRET experiments. FRET stands for Förster or Fluorescent Resonance Energy Transfer. Basically, what happens is that if you have two fluorophores nearby one another, if one fluorophore emits light of a wavelength, and remember, just when we're thinking about a wavelength, just think about energy. So if it emits light that has the energy that excites another fluorophore, so another molecule that can absorb light and fluoresce, if it excites that other fluorophore, then the fluorophore can kind of like steal the energy that the first one would have given off and then give off its own light. So when you shine light that excites the first one, what you're going to see is actually the emission of the second one. And so we'll get much more into detail about what's actually going on. But crucial to this is that it can only happen if the fluorophores are close. So when we're talking about close here, we're talking about like less than 10 nanometers. And remember that an angstrom is 0.1 nanometers. And so basically what this is going to be is about 100 angstrom. But that's like the maximum. So typically what we're dealing with is more like about in the 5 nanometer range. And as we'll see, you can actually calculate distances based on the amount of frets because it is distance dependent. So you can use it as a kind of like spectroscopic ruler to see how close together two molecules are, or to see how close together two parts of the same protein are. So it's kind of like you have two apartment buildings, and if their elevators are just lined up right, what can happen is that when one is going down, it kind of hops over to the next door apartment and takes the ride up to excite that electron.
So it's non-radiative transfer. So you're actually, the first one isn't even giving off the light. It's just getting transferred non-radiatively, not through light, to that second molecule. And this can only happen if they're really close together and their energy levels match perfectly, allowing for those little like wiggle vibrations and stuff. But you're not going to be hopping from one apartment building to the apartment building 5 blocks over, but maybe you can hop next door. So this is going to allow us to see if molecules are close together. Actual Jablonski diagrams will look something like this more. You can see that you have these different energy levels and you get this transfer of energy if the energies match between the light that's given off by the first one and the light that's absorbed by the second one. And remember that when we talk about the light that's given off or the light that's absorbed, so we're talking about our excitation and our emission, and we're thinking in terms of wavelength, which is going to be this lambda. So if you have a higher wavelength, remember that a higher wavelength is going to be lower energy. So let's just write that down so we remember. So we have higher wavelength, lower energy. And then we have lower wavelength, higher energy. So our donor is going to get excited. It's going to absorb the higher energy light, the lower wavelength, and then it's going to emit light. And this light that it emits is going to be lower than in energy than it, but it's going to be enough to excite the acceptor. And then the acceptor is going to give off even lower energy of light. The emission of the donor has to match the excitation of the acceptor. So you want there to be this like overlap in between them. There's various things that you want, like you want good brightness, you want good lifetime, and you really want to make sure that your excitation of the first one and your emission of the second one are going to be well separated so that when you shine light that excites your donor, you're not going to then detect that light. And you also want it so that the light that excites the donor isn't going to overlap with the light that excites the acceptor, or else you'd be exciting the acceptor, even if you didn't excite the donor. So basically, scientists have gone through a lot of trouble to come up with different combinations and different fluorophores, both fluorescent protein as well as chemicals, in order to try to optimize these various properties. A common combination that you might see is CFP and YFP, cyan fluorescent protein, and yellow fluorescent protein. And so you'll see things like this blue dotted line, or I guess the cyan dotted line, we have the CFP's excitation. And then the solid line, you have its emission. You can then see that its emission is going to overlap with the excitation of YFP. And then YFP is going to give off light of a longer wavelength, lower frequency. So what you're actually dealing with, though, is basically the part that they overlap. So you want the emission of your CFP to overlap with the excitation of your YFP. And so you can see that there is this range in which they overlap. So you can have different combinations of different fluorescent proteins and different small molecules, dyes. You need the emission of the first one to be near the excitation of the second one. And so often it won't be like perfect, like because it's talking in terms of the maximum, but remember we have that wiggle room, that more of a curve. But you want to see something where, say, we give off light at 520 and now this one absorbs light at 550. So the excitation from the first one is going to excite the second one. And there are a lot of options with a lot of really fun names. And often, instead of just trying to remember which one goes with which, you just look at a table and see which ones normally go together. Okay, so you have this choice of your donor and your acceptor, but the real key thing about FRET is that it's distance dependent. If those molecules are close together, then you can get FRET. You can jump from one apartment to another. But if they're far away, they're too far, you can't get that FRET. The closer they are, the higher the FRET, and the further they are, the lower the FRET, and to get to a point where you don't have any. This E, this is FRET efficiency, so how good that FRET is. And you can see that if they're close together, you get this really high FRET, and if they're far apart, you get the low FRET. Now, in the middle, at this like 50% mark, so this 50% mark, That's going to correspond to your R naught, which is the distance between them at which you get half of that FRET efficiency. This is also sometimes called like the Förster distance, the 50% transfer efficiency. Things get really complicated because it doesn't just depend on distance, it also depends on orientation and a bunch of other stuff like various properties of the fluorophores. Bottom line, you don't need to worry about that. But what I do need you to know is like, yeah, those complications are complicated when you try to like think about the math, but they're actually really great in that they allow us to figure out information about the molecules, not only how close together they are, but also their orientation, their movements. There's a lot of information that we can get just by measuring the FRET efficiency. One of the most important things is that distance dependence is like really distance dependent. It scales to 1 over r to the 6th, where distance between the molecules, this r. And then the R naught is basically the property of the fluorophore pair. What I just need you to know is that it scales to 1 over r to the 6th. So basically, as you move away, you're going to quickly drop off in FRET. And because there's this actual relationship that between them, there's actually a lot of variables that go into these numbers, but people can mathemize those variables and you can actually figure out the R, the distance between these molecules, just by measuring the FRET. And then remember this R naught, that was our 50% transfer efficiency distance. This is typically about 3 nanometers to 7 nanometers. The maximum that you can get and still see any FRET is typically about like 10 nanometers, which remember is 100 angstrom. And so because you have that mathematical equation, sometimes FRET's referred to as like a spectroscopic ruler. The closer they are together, the higher the FRET, the further they are, the lower the FRET. And so by measuring the amount of FRET, you're then able to determine how close together they are. A lot of these fluorescent proteins we talk about have these like little beta barrels. And so these beta barrels, a motif. And so each of these would be beta strands. And then you have this beta sheet that's kind of in this circle. And it looks kind of like a channel, but there's actually a bunch of side chains sticking in here so that the water can't get in. And this fluorophores is nice and protected, and it's able to do its shining. But it's also going to be big. And so we're already taking like 2 nanometers or so from our distance that we have. And remember, we only had about 5 nanometers. And so now we're saying, okay, well, like 2 of the nanometers is actually taken up by the protein itself. So that's one of the downsides about protein sensors, is that they're kind of big. And not only does that make the molecules have to get closer in order to see them, but it also means that you could have, if you put a big molecule onto your protein, that might actually affect how your protein is functioning. Small molecules, here's an example, Psi3, this is a common one. You also see things like Psi5. This is Psi3, it is maximally excited at 550 nanometers, and it's emissions at 570 nanometers. So if you were to go and want to use Psi3 as a FRET donor, so that first partner in the pair, what would you want to use as your acceptor? Not a specific name, but what would you want its absorbance to be? You'd want it to be around 570 nanometers because that's what this Psi3 is going to give off. So why don't you pause the video and think a little bit about some of the benefits and drawbacks of both small molecules and fluorescent proteins. With small molecules, well, they're small. So there's less risk of interfering. Can detect longer distances. Between molecules. It's not that the fluorophore itself is that, but it's basically because you don't have that bigger, you don't have to consider the size of the protein taking up some of that distance. They're more stable, but they also have downsides. So let's think about what are some of the benefits of having a fluorescent protein. Probably the main benefit is that you can be genetically encoded. So basically, we can attach a GFP, we can attach a YFP, we can attach a CFP onto the ends of proteins. So we can attach it to the N terminus, or we can attach it to the C terminus, just by sticking the sequence for that protein onto the sequence of our protein, by making one of those fusion proteins. Now, you can't genetically encode the instructions for putting on site 3 or putting on one of those small molecules, at least within the cell, but you can genetically encode the instructions for making that fluorescent protein. So that is one of the main benefits of having a fluorescent protein, is being able to get cells to attach it to proteins when those proteins are actually made inside of the cells. We're able to monitor what's going on inside of cells and even maybe inside of organisms. So that genetic encoding of those fluorescent proteins is really, really going to be a huge benefit. But those small molecules are really helpful too, similar to FRET, but without giving off fluorescence at the end. There's this thing called quench fluorescence. What happens here is that second molecule is going to absorb that energy from the first molecule. It's going to do that whole FRET stuff with the first one, but it's not going to actually give off light. Instead, it's a quencher. So it just absorbs that light, but it doesn't give it back as light. So yes, it's going to give it back as like heat and all that boring stuff, but it's not going to give off light. So what happens if you shine light that excites the first fluorophore, you're not going to see any emission if they're close together. But if they go apart, then you can see that emission of the first one. Remember, the quencher doesn't have an emission. And then this way you can detect whether the molecules are interacting, whether they got separated, that sort of thing. So here's an example of a quencher. This is a common one. It's called Dabsol. And you can see that you're only seeing an excitation wavelength, not an emission wavelength. It can absorb this light, but it doesn't give anything back that you can see.
To review, different molecules absorb different wavelengths of light that correspond to different amounts of energy needed to excite electrons. These differences are going to be different for different molecules, and so different molecules will absorb different wavelengths of light. The wavelengths of light are providing the energy to excite the electrons to a higher energy level. When they get to that higher energy level, eventually they're going to have to come back down. They might just fizzle it off as heat, bump into things and stuff, or they might give off that energy as light. And when it gives it off as light, we call it fluorescence, which is a form of luminescence in which no matter how the electrons got excited, when they let off that energy, they're letting off some sort of light. We call that luminescence. In the case where the exciting energy came from light, we call it fluorescence. Different molecules will get excited by different wavelengths of light and will emit different wavelengths of light. There are a variety of different protein and small molecule fluorophores to choose from, and you can design a lot of really cool experiments to figure out cool stuff. Some of the most cool experiments you can do involve FRET, Förster or Fluorescent Resonance Energy Transfer. Here you have two fluorophores, and one of the fluorophores lets off light, or it would let off light at an energy level that excites the second fluorophore. If they're close enough, the two fluorophores, then what can happen is that what would have been light that's given off by the first fluorophore gets transferred to the second fluorophore, and then the second fluorophore gives off light. And the light that you see is going to correspond to the light that the second fluorophore gives off, not the light that the first fluorophore gives off, even though you've shown a light that excited the first fluorophore. By placing fluorophores on different molecules, you can see if they interact. You can put fluorophores on different sides of the same molecule to see if they are close together. So you can do things like measure conformational changes in protein, because FRETs can serve as a sort of molecular ruler, because there's a very high distance dependency where you can actually calculate the distance between molecules based on how efficient the FRET is. There's also a method called fluorescence, where here, instead of having two fluorophores, you have one fluorophore and a quencher, and the quencher is going to steal the energy that the first fluorophore gives off. Instead of seeing light, you're not going to see anything, even though the first one is getting excited. And you can use this to see if molecules are close together or far apart, similarly to with FRET. But in this case, you will see light if they're far apart and no light if they're close together. But you'll see the light that was given off by your first fluorophore because, well, there is no second fluorophore. You just have a quencher. We'll look at examples of this in the future.